All right. So a lot of, like this book, I don't like the order that it does stuff in. And so it sort of just shows you the unit circle. And it's like, here, take it. But I don't like that because I really want you to know where the stuff comes from. All right. And so where the unit circle actually comes from has to do with special right triangles. Special right triangles, which are from geometry. Special right triangles. So I have an isosceles right triangle. Side length 1. What does isosceles mean? Two sides are congruent. Yeah, two congruent sides. Okay. And it's a right triangle. So I'm going to just draw a picture of that. We'll pretend those are straight lines, and we'll also pretend that they're congruent. All right. And then that third side. So we have two congruent sides. And, well, if the two sides are congruent, what else do you know about that triangle? The base angles are congruent. Very good. That is another thing from geometry. So these two base angles have to be the same as well. And if those are the same, then that means they are how many degrees? Good. All right. So 45 degrees and 45 degrees and 90 degrees gives us 180 degrees in our triangle. And so that is one of the special right triangles, which is a 45, 45, 90 triangle. Now, we have a side length of 1, which means here our side length is 1, and because they're the same, that one's also 1. Can we figure out the third side by doing the Pythagorean theorem? So that's going to be 1 squared, leg squared, plus leg squared equals, I'm going to say this is r. R squared, we're trying to figure out r. 1 squared is 1, and 1 squared is 1, so that makes 2. And then I need to take a square root, so we get r equals radical 2, square root of 2. All right. So it turns out that every 45, 45, 90 triangle has side lengths that boil down to these numbers. So, for instance, I can dilate this triangle. Dilate your pupils, they get really big, right? So I could dilate this and I could say, hey, let's make a triangle 5 times bigger. Well, if I make my triangle 5 times bigger, all I'm doing is multiplying every side by 5. So 1 times 5 is 5, and 1 times 5 is 5. And 5 times radical 2 is 5 radical 2. It's still a 45, 45, 90 triangle. It's just bigger. And we can do that all day and night. Now, what's really interesting about every single 45, 45, 90 triangle is that I can now ask questions about, hey, what's the sine ratio according to our 45 degree angle? So let's use our little triangle here. Looking from our 45 degree angle, what's the sine ratio? What? Okay, so opposite over hypotenuse would be 1 over radical 2, and then you all rationalize that, which is what I was hearing. So we have to rationalize because we don't like radicals in the denominator. And we get radical 2 over 2. Do we get the same thing when we use a big triangle? Yeah, you do, because it would still be opposite, which happens to be 5 over 5 radical 2. And what happens to those 5s? They cancel, they reduce. And so again, we're back to 1 over radical 2, which again, we would rationalize and get radical 2 over 2. So it really doesn't matter how big or how small our triangles are. If it's a 45, 45, 90, those sine, cosine, and tangent ratios are always going to boil back down to these nice small numbers. Okay? Kind of interesting. What is the cosine ratio according to our 45-degree angle? Adjacent over hypotenuse, so 1 over radical 2. And then if you rationalize that, it is going to be radical 2 over 2 again. Now I switched here. What's pi over 4? Radians or degrees? Radians, okay. But still, pi over 4, let's think about it. What's pi? 180 over 4? 4 parts of 180. How big is each part? 45. 45. Hey, look at that. This is 180 divided by 4, which is 45 degrees. Okay. So really, same question. This is the tangent of 45 degrees, or the tangent of pi over 4. Tangent is opposite over adjacent. So 1 over 1, which is just 1. Okay, nice. Okay. So special right triangles is kind of cool, and we can make that triangle any size we want by multiplying or, in fact, dividing, okay? And so now we move on to the unit circle. So you might want to, yeah, so get your, no, not really. Go ahead and trace your circle. Trace your jam jar lid. So you have a nice good sized circle. And go ahead and create your X and Y axes. I'm trying to do this as quickly as I can. It's hard. I like to talk, you know. All right, I see people drawing their x-axes in. And y, yeah, you can go ahead and do your x and y axes on there. Because what I have here is my ladybug. And my ladybug has a dream to be in the circus. And because of that dream, she needs to learn, well, it could be he, right? He needs to learn. They need to learn. Very good. Putting your trombone in. Okay. They need to learn some positioning. All right. They need to be trained how far to walk. Well, right now, my ladybug is learning how to walk in a circle. A really perfect circle, in fact. And this isn't just any circle. It happens to be a unit circle. And what do you suppose I mean by a unit circle? A single unit circle. So what do you think I mean by a unit? What's the radius? 1. Okay, so my radius is 1 unit, and maybe it's 1 foot. I don't know. Or maybe it's 1 yard. Or on your paper, maybe it's 1 inch. Aren't units kind of ambiguous?
Yes.
Because they all have a unit of 1, right? But they're all different measurements. Does that make sense to you? Is that weird? Or it's kind of funny, isn't it? Okay. So this has a radius, my circle, because this is the center of my circle. It's also the center of our coordinate plane. Has a radius of 1 foot. And yours might be 1 inch. But it's still 1 unit, right? Okay. So right now, my ladybug is starting right here where we like all things to start. At this ordered pair. What would that ordered pair be where she is sitting? 1, 0. Yeah, you're good with that, right? And so what we need to do is we have to create for my ladybug some traveling distances. So she's going to go a particular length t. This is her travel. Oh, I'm out of ink. Her travel distance, t. And for each traveling distance, I want to have P of t, where P of t is a point, not y, sorry, x. I don't know what I'm doing. There we go. X, y is a point on our coordinate plane. So we want to figure out traveling distances for my ladybug and where she will land if she travels that far. Well, her path that she's traveling on, her path is along the rim of the circle here. All the way around that circle is a measure of what? Circumference. Very good. Circumference. What is our formula for circumference? 2 pi r. Very good. And what is our radius? 1. And so my ladybug, in this case, in my case, your case might be inches, but in my case, my ladybug to travel all the way around the circle, she goes 2 pi feet, and she would land back at the same point, right? Okay. So if she travels 2 pi feet around my circle, she's going to land back here at 1, 0. It's also true that if she goes 0 feet, isn't she going to stay there at 1, 0? Yeah? Okay. Good. All right. So she's going 2 pi radians, or feet rather, and gets all the way around and lands at 1, 0, but also 0 feet. She's still there. Okay, let's see. I want her to be able to land right here. How far does she travel to get to here? 1 pi. Yeah, 1 pi. That's halfway around our circle. Not 2 pi, but 1 pi. So if she goes pi feet, what point does she land at here? Negative 1, 0. Good. All right, let's see. Well, wait a minute. So now she's learning a new trick. Not only can she go in the positive direction, but now she can go in the negative direction, right? Okay. So she could turn around and go the other way now. So not only, let's see, I want her to land here. So how do we tell her to turn around? Negative pi. Okay, so negative pi would also land her at this spot here, negative 1, 0. Okay, very good, ladies and gentlemen. Negative 1, 0. Okay, she's getting really good. She really loves her Cheerios. Just checking to see if you're paying attention. All right. That's how you train your kids, too. You just feed them Cheerios. We really like those. Okay. Cheerios works for all kinds of things. Okay. Now, Ladybug needs to land right here. How far does she travel to get to this point? Yeah, half of pi, or pi over 2. Yeah, half of pi, or pi over 2. Very good. And what is this point here at pi over 2? 0, 1. Very good. 0, 1. Because right here is 0, 0. So that is up 1. Right? Okay, very good. All right. Now my ladybug wants to go all the way around the circle and stop right here. How far has she traveled?
3/4.
Okay, I hear two good answers. Let's see, if this is 1 pi over 2, this would be 2 pi over 2, which reduces to pi, and this would be 3 pi over 2. Good. So 3 pi over 2 lands her at this point. What point is this? 0, negative 1. Very good. Okay, so 0, negative 1. I also heard another answer. What if my ladybug wants to get there really fast?
Oh.
Negative pi over 2. Very good. So she could just turn around and go pi over 2 feet in the other direction, right? So negative pi over 2 also would land me there. Okay, excellent. Well, my ladybug is doing really, really good now. See what I did there? Okay. All right. So now we're getting more complicated, and now I want my ladybug to only go this far. Ha, very good. Pi over 4. Very good. So if we take pi and divide it into 1, 2, 3, 4 equal sections, then she is right here, and that is that distance of pi over 4 that she's traveled on my circle. But now our trick is, hey, what is that ordered pair? So what is pi over 4? How many degrees is it? 45. Yeah, we just talked about that. So pi is 180 divided by 4 is 45. So that little angle that we just created here is a 45-degree angle. So if I get really clever, I can drop an altitude. Whoop. So we're going to drop an altitude straight down, always, always, always to the x-axis. And we turned our angle into a triangle that hopefully I can figure out some information on. I know that it is a 45, 45, 90 triangle. And so since I know that it's a 45, 45, 90 triangle, what do I know about these side lengths in a regular 45? 1, 1, what's the other side? Radical 2, right? We just did that. Okay. Now my problem is this triangle is a little bit too big because radical 2, the square root of 2, oh, sorry, let's see. There we go. The square root of 2 is 1.414. And so this hypotenuse lines up with this length here, but how long is our length here in our circle? It's 1, right? Because it's the radius of the circle. Okay. So this is too big to fit here. And so I need to do some magic to make it a little bit smaller. I need to morph this radical 2 into a 1. What can I do? Divide by?
Pi over 2.
Divide by radical 2. Divide. Now if I divide one side, I have to divide all the sides. What is radical 2 divided by radical 2? 1. And here we have 1 over radical 2, which we would rationalize. So it would turn into radical 2 over 2. And again, 1 over radical 2 rationalizes to be radical 2 over 2. And so what we see here in this triangle is this new length here of our shrunken triangle. This horizontal leg is radical 2 over 2. Well, that corresponds to this horizontal leg here, which is our x value. All right, radical 2 over 2. And then how high vertically do we have to go? Radical 2 over 2. And so it turns out for every pi over 4 triangle, we get these numbers for the legs, radical 2 over 2 and radical 2 over 2. Okay, they're the same, right? This leg must be congruent to this leg. So the numbers match. It's kind of nice. Okay, so now my ladybug can travel pi over 4. How far does she travel to get to this point? 3 pi over 4, yeah, 3 pi over 4 or 3/4 pi. How do we get that? 1 pi over 4, 2 pi's over 4, 3 pi's over 4. All right, so she traveled a distance of 3 pi over 4. And again, I want to know this ordered pair. And so I'm thinking to myself, hey, I can drop a leg. Altitude, perpendicular leg. Always, always, it comes to the x-axis. Now, 3 pi over 4 is 135 degrees. All the way to here is 135 degrees. Well, what we create when we drop a leg is we create an angle that's called the reference angle. So this little angle the reference angle is between our terminal side and our x-axis. So this little angle is called a reference angle. And how big is it? Another 45 degrees. So this is an identical triangle. It's just in quadrant 2. So now, what is this x value? Radical 2 over 2, but is it positive or negative? It's negative because we are left of 0. So negative radical 2 over 2. And the y value? Positive radical 2 over 2. So now all we're thinking is, what quadrant are we in? And that's just going to change the signs for us. All right, so my ladybug's getting really good. Now she also is going to do some work down here. So how far does she travel to get to this point? 5 pi's over 4. Let's count. 1 pi over 4, 2 pi's over 4, 3 pi over 4. This is 4 pi over 4, which makes this 5 pi over 4 feet. And again, we could drop an altitude if we want to. Now in this one, we drop up to go right back up to the x-axis. And again, what we create is called a reference triangle because this angle is very big. It's over 180 degrees, right? And so what we reference is this little angle between the terminal side and the x-axis. And how big is this little angle? Yeah, 45. So a reference angle or reference triangle, which is what this is always an angle less than 90 degrees, which is kind of nice. It's easier to keep track of things that are smaller numbers. So this little reference angle, again, is a 45. So we know that the legs are the same. What ordered pair gets us down here in quadrant 3 then? Negative radical 2 over 2 and negative radical 2 over 2. Good. All right, last one. How far does my ladybug travel to get to this point right here? 7 pi's over 4. Because all the way around would be 8 pi's over 4. 8 pi's over 4 is 2 pi. And so again, we create a reference triangle. If you want, you don't have to. But it's right there, little reference triangle, reference angle right there. How big is that reference angle? 45 again. So we know it's a 45, 45, 90. And what is my ordered pair that gets me in quadrant 4? Good. Radical 2 over 2 and negative radical 2 over 2. Ladies and gentlemen, good job. I lovingly call these the bow tie triangles. Do you see the bow tie? Okay. All the numbers are the same, right? Radical 2 over 2. What's the only thing that changes? The signs, negative and positive, and that's based on the quadrant that you're in. Okay, very good. So one last thing here that's so important. If I were to now ask you, hey, what is the sine of pi over 4? Well, pi over 4, we know, lands right here. And that creates our little reference triangle that we have drawn right here. I have this leg along the x-axis. That is length, radical 2 over 2. And the vertical leg here, also length, radical 2 over 2. What's the hypotenuse? 1. So if I want to find the sine ratio, what would that be? Yeah, radical 2 over 2 over 1. Huh. So it's just radical 2 over 2, isn't it? In fact, well, cosine can be the same, right? Because the hypotenuse is 1. It's not changing anything, is it? Okay. So it turns out cosine of pi over 4 is also radical 2 over 2. The y coordinate gives us the sine value of our trig function, and the x coordinate gives us the cosine value. It's alphabetical, cosine, sine, okay? Which is super nice. So if cosine of theta equals the x coordinate and sine of theta equals the y coordinate, that's really useful. But how do we figure out tangent of an angle then? So tangent is sine over cosine, isn't it? Sine over cosine. Sine over cosine would be y over x. Okay, so we can use these ordered pairs to find all of our trig functions. Kind of interesting, okay? Which is super cool. All right. With that knowledge, we have a few questions to answer, and then you get to go on. All right. Find the exact value of each trigonometric function. Find the exact value. Find the exact value. You'll notice I said exact. That's pretty important because exact means I don't want you to plug it into your calculator and give me a decimal that goes on forever. That would be incredibly inaccurate. All right. That doesn't mean to say that you can't do that to check your answer, because you certainly can. For all of these kinds of things, I'm always going to draw a little picture. I call it circles and dots. If you have these things memorized, fantastic. If you don't have them memorized, circles and dots works really well. So we're going to do the cosine of 315 degrees. So I'm going to create a very small little axis on a little circle. My picture is about quarter size, in case you were curious, on my paper. All right. All right, we want to find the cosine ratio according to a 315 degree angle. So 315 degrees, there's our initial side of our angle. Where does 315 degrees fall? Which quadrant? Fourth quadrant, yeah, very good. So it falls right here. And when we see that angle, we have to go to the reference angle. The reference angle is right here. How big is that reference angle? 45. Very good. 45. All right. So you know that's a little 45 degree angle in there. Since we know it's 45, what is this ordered pair in quadrant 4? Radical 2 over 2 and negative radical 2 over 2. And so cosine is which coordinate? X. So that's going to be the positive radical 2 over 2. All right, these ordered pairs are alphabetical. Cosine comes before sine. Cosine, sine, cosine, sine. All right, so it is that x coordinate that we take. Let's look at sine of 9 pi's over 4. Sine of 9 pi's over 4. So again, I want to draw my angle. And what do we, where's pi? 180. And what do we need to cut pi into? 4 pieces. So there's 2 and there's 4 pieces. And whatever we do to the top, we do to the bottom. And then we get to count around. So here's my initial side. 1, 2, 3, 4, 5, 6, 7, 8. Pi's over 4 gets us all the way around. So 9 pi's over 4 lands right here. And what is that ordered pair? Radical 2 over 2 and radical 2 over 2. Sine is the x or y coordinate? Y coordinate. So it's radical 2 over 2. Sine, because sine is the y coordinate.